On Saturday, we started with pattern recognition. For pattern recognition, two themes that we will discuss in this workshop are clustering and dimensionality reduction. We realize that pattern recognition often can give us a lot of insight into data. We took the example of San Francisco city. If you were to rise above the city, you would see its structure. You would see where the financial district is, where the Golden Gate Park is, where the residential areas are, and they are clustered. They come in clusters. And we talked about the fact that clusters are very common in nature. Wherever you look, you see clustering of data. In fact, uniformity in data is much harder to find. Clustering is quite common. You look up at the sky and you see clusters of stars. So you look anywhere, you look at people at a social gathering, you find them clustered. So clustering is everywhere. How do we detect clusters then? The algorithms that detect clusters are called clusterers. Now, there are many types of clusters out there. And obviously in one workshop, you cannot cover all of them. We'll cover three core areas of clustering: k-means clustering, hierarchical or agglomerative clustering, and density-based clustering. K-means and hierarchical are both there in chapter 10 of your textbook. Density-based is not there, so it will be, I'll give some other material to study that. Now, when it came to k-means clustering sort of solves, in some sense, half a problem. It says, tell me how many clusters you want to find. And then the algorithm goes and finds those many clusters in the data. Now, whether that number is right or wrong, it will nonetheless find those many clusters in the data. That is the risk of that. In the absence of, like you can't visualize very high dimensional data. So it becomes, you don't know whether that clustering is correct or not. So in order to know whether that clustering is right or not, you have to take a mathematical measure. There are many measures, but one measure which is quite common and in fact mentioned in the textbook is WSS. So to set up k-means clustering, you need two things. You need, of course, the data and the number of clusters predetermined that you are searching for. And you need a distance metric. You need to be able to define what is the distance between 2 points. Quite often we assume Euclidean distance. It need not be Euclidean. It could be any other form of distance. So long as you can define a distance between 2 points, you could go about doing clustering. So this is a little bit of a technicality that I don't think I covered. What is a distance? How do you define distance between 2 points? Distance between 2 points is, in a more general sense, it is, and let me start with that today before I review the rest. Distance between 2 points. Let me make it a little bolder. Yeah, it is bold. Distance between 2 points. Xi and Xj, obviously assume that they are vectors. It is a function. You realize that distance is a function that maps this point Xi, the pair of the points Xj. And I'm deliberately starting from a more abstract place. It maps it to, distance is a function that maps it to a real number. Are we together? And real plus, actually. In other words, distance can be 0 to infinity. Distance can never be negative. So that is the first definition, first aspect of a distance. Distance between 2 points, Xi and Xj, must be greater than and equal to 0. The second part, obviously, and you would imagine geometrically, you can imagine that this Xi, Xj, distance between 2 points is equal to 0 if and only if, so this word is a mathematical notation of if and only if if and only if xi is equal to xj. Means in the space, in whichever space you're representing these points, these two are essentially sitting on top of each other. Then only can the distance between 2 points be 0. Right? So if you geometrically think of a space, and this is xi, and this is xj, the, the distance is this. Now comes an interesting third part of the third condition that you need to define distance. There are many such functions that you can do. First, also, this is true. Xj, xi is equal to distance xi, xj. Right? So it's symmetric. It's a symmetric positive number, 0 or positive number. But there's one extra thing that you need for distance. Suppose you take a point xk, then you would agree that this path is longer than the path from xi distance, like let me just call it A, B, C, right? A plus B will always be greater than equal to C. Would you agree? In the asymptotic limit, this point could be here, literally, the K can be here, in which case it will become an equality. But in general, A plus B is a longer path than C. Right? And any function that fulfills these requirements, namely, we can say that if xi xk plus d xk plus xj is always greater than equal to distance from xi to xj. Right? In fact, the shortest distance, and here I'll bring in a new word today, the shortest distance, once you define a notion of distance, these are your conditions. This is how distance is mathematically defined. And if you go back and look at Minkowski distance, you'll see that it fulfills these identities, these relationships, distance function. Distance is sort of a function which fulfills all of these conditions. It is positive, 0 or positive. It is 2 points have 0 distance if they are the same point and they're symmetric. At the same time, the distance between the straight distance between 2 points, this distance C, there's a name for it. It is called, let me use a bolder font. It is called, now let me use something else. It is called geodesic. It is defined as the shortest distance between two points. Now, you would say, well, why is it not a straight line? And the example that we took last time is, if you think of the Earth, for example, and even if you're looking at sort of a locally this thing, so then the distance between this point here and some other point here is not the distance through the center of the Earth, because that distance you can't actually travel. You're living on the surface of the Earth. So what will you have to do? Your distance will in reality be what is called the great arc, right? It is, you have to walk on the surface of the Earth and find the straight distance from here to there. And that distance is a curve. It's not a straight line. Right? So this is something, a bit of a learning. See, as you go into machine learning, inevitably it uses mathematics. So then one has to become gradually familiar with how mathematicians think. Mathematicians actually think in terms of generalities. The moment they see something, the first question they have quite often is, how can I generalize this into a broader theory? Right? So we think of distance as Euclidean distance. So now we got introduced to Manhattan distance and other distances. But then you can ask a much more generic question, general question. What in a sense is distance? And the moment you realize that a distance is a function that takes a tuple and maps it like this, then it opens the door to asking the question that what is the shortest path between 2 points, right? So is it always a straight line? It is not. In non-Euclidean geometry, it is not. And so that brings us to the to the notion that the right term is not a straight line. You shouldn't use the word straight line, but you should use the word geodesic. And as you do, as we go around and make a progress in this workshop, and we get into, for a couple of sessions, not always, but we'll have to deal with topology and things like that. So remember this point that I mentioned, that geodesic is the right appropriate term for the shortest distance between 2 points, and it need not necessarily be straight line. Right? So it's a review. Now, going back to what we were talking about last time, once you have framed the problem as I have a distance measure, I have a number of clusters that we need to find, we have fixed. Then it is straightforward. We use this process of iteratively finding it, randomly pick those, let's say k is equal to 2, randomly pick 2 points and declare them to be centroids. Then what you do, then you go through this iterative process, assign all other points to its nearest centroid, and then recompute the centroid of each of the clusters. So you'll end up with clusters and then recompute the centroid. And you keep on doing it till you notice that in a very intuitive sense, the centroids stop drifting. Right? Now, drifting is an intuitive term. What does it mean in programming? It just means that the centroids are not moving around too much. Like, they are within an epsilon distance of the previous iteration centroid. That's one way of looking at it. Another way, which is equivalent, is to say that not many points are switching loyalties between the two centroids. Right? So that's what it is. Now, we went through this process iteratively, and we did notice that it does converge pretty reasonably. But there are two problems. Their pathology is, what if you end up sitting at the, just by absolute bad luck, the data is such that there's a trap in it, and you just fall straight into the trap. You end up picking points A and B in such a way that the centroid now, the centroids you find, or the clusters that you find, are stable clusters, and they are not good clusters, right? They don't have cohesion. You can actually see that you have taken half of one cluster and half of another cluster and called it a cluster, and likewise for B, you have taken half of one and half of the other, and real clusters, and call them a cluster. So how would you know that you shouldn't do it? There's a measure of cohesion, which is within cluster, some squared distance. So for each cluster, find all pairwise distances, square it. Don't bother taking an overall square root later. Just take the square root and average it out, and then see what did it come to, and then repeat it for the next cluster and add up all of these measures. The smaller the WS is, the more tight-knit, the more sort of thick the cluster is, the more bigger the WS is, the more it is a sense that there are too many distances, big gaps between points in the cluster. And that's why you know that if the top half is a cluster, for example, you see points from the one real cluster to the other real cluster, there will be large distances. Because there will be large distances, your WSS will explode. And that is a clue. So now you ask this question, well, how do I avoid this situation? So there are multiple heuristics that people do. One of them they will do is they will pick a point, and then the second point they'll pick as far from the first point as possible, so that you don't end up in this situation where you end up creating bad clusters. That is one way. None of these things, to my knowledge, guarantee that you won't have bad situations. The gold standard, of course, is in practice, it works. Most of the people, they understand their domain, and in most of the domain, where to start. For example, in realistic terms, you get data, you get a new refresh of data. What is a good starting point for centroids? Well, pick the centroids of last week's data, because the data would have shown some drift. But essentially, last week's true clusters are not a bad choice to start with for this week's clustering. You'll quickly converge because you have started pretty close to the real answer. Right? Or if you get data fresh, you can try these heuristics, most likely once it works. If you have the luxury of not big data, not terabytes of data, then the gold standard is run this algorithm many, many times and pick that particular run's cluster discovery, which gives you the lowest WSS for the same value of K. That is that. it still leaves. And so there are other methods people use. In practice, as I said, a lot of it becomes moot because in real life, the experienced teachers, whatever you do, the first time it is exploratory, but soon you figure it out. And by the time you're productionizing it, it gets a lot easier. You have a pretty good intuition into the data, and you have a good sense of where to start from. So you don't randomly initialize, you initialize where you know that you'll quickly converge. That's an important fact, actually, that choosing your initial point often can decide how quickly you can converge in k-means clustering. Now comes the second point. What it leaves all of this is the hyperparameter k. We don't know what k is. How would you know what is the best k? Oh, excuse me, guys. There's a small meeting. I'll take a, can I please take a 2-minute break? So we still have to determine what is the best WA, what is the best number of clusters that you have. And the answer is not perfect. K-means clustering, its great virtue is its simplicity. Its weakness is that it gets harder to determine what the real clusters are, especially if the clusters are not globular. In other words, they are not convex shaped clusters. So with all those limitations, nonetheless, there is a way. What you do is you start plotting the k for various values of k from 1 to n. You start plotting the WSS. Now you don't go to the complete limit of n being the number of points, because then you know WSS will be 0. You stop quite early, but what you do is you plot the WSS for a given value of k, then the next, and at some point you'll discover an elbow, and then you may increase it by a couple of more points just to be sure that the elbow that you saw was genuine. If you see an elbow, it is a very good sign. It means that you have found what is the optimal number of clusters generally. Now, you may not see this. The plot can be worst case situation. It could be like this. When it is like that, it generally means data has very faint or non-existent clusters. It could mean, or it could mean that the clusters that exist are not roundish clusters. They're not convex shaped clusters. Right? So either of the two may be true. So you have to go and try other approaches. But this, we're looking for the elbow, which is the elbow method. And this kind of a plot is called the scree plot. What we have just built is the scree plot. And with that, I believe we have essentially a review of last time. Any questions before I start with today?
Yeah, Asif?
Yes.
So you mentioned that you start with the prior week centroid, right? And you kind of use that as your starting point. What if there were new clusters that were formed? So how does that help? I mean,
yeah. There is always a risk, because see, if new clusters have been born and the K itself has changed. So what you do is, whenever you are in a hurry, like for example, incrementally, you do it. But then once a month or once in 2 3 months, what you will do is you will watch out. Depends on the situation, how adverse it is not to discover a complete radical change in data. See, changes in data emerge slowly. They don't just happen in most real situations. So then what you do is you run the k-means clustering from scratch, and you do that whole elbow plot method and you cross-validate. That is one thing. But having said that, see, in practical terms, what happens is k-means is only one algorithm. It's the simplest. What we do is, and I'm going to tell you another algorithm which I use much more, where a k is automatic. You discover what the real number of clusters are. Right? So k-means is something is good to do, is cheap, but whenever it gets important or serious, well, there are other methods that are far more, in many ways, reliable. Mm-hmm. And we will learn about those today. Having said that, k-means is still very popular, given its extreme simplicity. It's a very simple method. It is often used in production and in the industry. Any other questions, folks, before we go into the next clustering, which is the hierarchical clustering? In your book, it's called the agglomerative clustering. So I'll stick to the term, the hierarchical clustering is more commonly used in the industry. You'll see why the word agglomerative comes in here. Now, this is a different clustering method that is often, in many ways, people feel is more intuitive and gives you more freedom, but it is computationally much more intensive than k-means clustering. So the way you do that is, suppose you have data points. You take all the data points. Suppose imagine, let's start with some real clusters and you'll see this happen. So suppose you have clusters like, well, this color is terrible. Where's my white color gone? No, well, this better. Okay, and this better. Okay, so I hope this white color shows through properly now. So suppose you have a cluster like this, and you have another cluster, which I'll call like this. I've deliberately given two different colors. It doesn't mean that there is any distinction. In reality, you wouldn't know. You'll just get data in the feature space. What you do is you take a point, you take an arbitrary point. And so suppose you take a point here. Let me take a point using this color, this point. Now, what you do is you arrange all other points based on nearness to this point. You find, given this point, you find its closest neighbor. So you sort this list of points. Where am I going back to this? You take the list of points and imagine that you're making them in a sorted order. They're lined up in a queue. What you do is you just sort and find the nearest neighbor for this point. And suppose that turns out to be this. You put it here. You connect these two. You say, these 2 points are now connected. Then you take the next arbitrary point, whatever it is. Maybe you'll pick some point somewhere, and that also will have a nearest neighbor. Maybe it has 2 nearest neighbors at the same distance to each other. Happen chance, it can happen. So you put these 2 together. Are we together? And then what you're doing is these are consumed. So you keep removing those points from the list. Then the points that remain, you again pick some point and then you join them. You have another, let's say that 4 points are all at the same distance to each other, or 5 points, and you sort of join them, right? And so you keep doing this process till you have exhausted this list. So you notice what we are doing. We just picked a point and then found its closest neighbor. Then we represented it in this visual way, imagine. This visual representation, by the way, is called a dendrogram. So this is your first, if you're being introduced to this concept of dendrogram or this visualization, then welcome to one of the most effective visualizations in machine learning. Very, very effective, heavily used in research communities, especially in medical research communities and so forth. So this is it. Now, suppose you have exhausted all the points. Now comes the question that, and remember, so suppose I were to ask this question. If you look at this point, what is its nearest neighbor? Let me name these points: A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R. So if I were to ask this question, that what is the closest neighbor to D? What would you answer? What would you answer as the closest neighbor to D?
C.
You would say C, isn't it? However, if I were to ask what is the next closest neighbor to D?
Say E. Then you would say E.
Actually, no, you don't.
Any of E, F, G, H, I?
No, any one of these things that are here on this list could be. It is just an accident that I started putting E, F, G, H, I cluster next to CD because I was randomly picking up points. So this is a trap. Never.
But didn't we order them, Asif? What was the sorting order?
Okay, let me repeat the sorting order. You first put an arbitrary point A, right? So you have this list. So let us say that you have this list A, B, C, D. Let me put this list in some ridiculous order. So all the way to R, A, D, C.
Maybe in a brighter color.
Oh, brighter color. Okay, let's see. So let me use, okay. You have the numbers as R, A, D, Q, K, M, C, E, J, what did I miss? N, Q is already done. A, B is missing. B, C, D, C is here. D is here. E, F, E is here. F, G. Oh, G is done. No, G is not done. G, H. Where is H? H, and I, and L, M, maybe M, and N is already here, I believe. O is here. Oh, P. There is P somewhere here. No P's. Maybe I'll stick a P here. P, Q, R. All of them are there, right? So suppose you have this list of points in your data. What you do is you arbitrarily pick A. So is this visible, or I should redraw it in brighter colors?
Right, it's visible.
It's
no
visible.
worries.
Yeah.
Visible.
Yeah, we can go on with that.
So let's say that we pick A. So A is where? A is here. We take A out. Now the question we ask is, what is the closest neighbor to A? And then it turns out that you compare the A's distance to every point, and then you realize that it is B. So you take B out, and now B is here. You form this group. Are we together? Now, arbitrarily, you take the next point. You say, okay, let me pick a point. For whatever reason, you pick M. Let's say you picked M here. And then you ask M, what is the closest neighbor to M? It is L. Let's remove L, right? So you form this group. Now, how many points remain? You go and say, all right, let me pick some random point. Pick a point, guys. What would you like to pick?
E.
P.
E. Because it have 4 neighbors as per the dendrogram.
Oh, E. Okay. So let's say that you picked E, right? So we'll take E out. Here, E. It turns out that it has 4 neighbors, all of them equally spaced apart. So F, G, H, I. So where is F? There we go. F, G, H, and I. Do you see how this list is getting shorter and shorter? And you create this thing. Now arbitrarily pick another point.
So Asif, one thing that's happening here is, like when we see E, F, G, H, I are a cluster, or we kind of put them into a group, it's not necessary that they were the closest. They were the closest of what is left of ungrouped points.
No, they are the closest. The reason is that if suppose the distance of E to B was shorter than the distance of to F and G, you realize what would happen? A and B would catch it. It would have
okay.
into AB cluster.
Yeah. Good point. Yes, missed that.
Right. So you see that what we are doing is we are arbitrarily picking points and we are creating this sub groupings. This subgroupings, and so the way you say it is that step 1, each point is a cluster. So the way you say, let me write this algorithm into its steps. Step 1, each point is its own cluster. So how many clusters are there? Total number of points, isn't it? Would you agree? If each point is a cluster, then the total number of clusters is the number of points available. Step 2, do the first agglomeration operation. You did that and you formed this. But now comes something interesting. Let's say that A and B or EFGHI. Let's go back to this picture, and let us say that for whatever reason, let me find some points which are very, very close to each other. Okay. Let's say that this was the EFGHI subgrouping. Now what you do is you have a cluster, you find its center, and I will leave the word at this moment open, find its center. And so for each of these points, each of these little clusters, you find their center, right? And so now what you have is a second order, and treat it as a point is as a new point proxy for its cluster. So what you do is you go and replace all of these points, and you say, hey, these points are represented by this point, which this pink point, which happens to be the center of the EFGHI. Right? And so you can repeat this process, and what you will end up with 1, 2, 3, 4, 5, 6, 7. You will end up with just 7 points, right? In this particular case, I started with very few data points, but you will end up with points. Let's say that you end up with something like this sort of situation. I just simplified it down to 7 points, 7 pink points. Those 7 pink points that you have, which represent obviously these clusters, 7 clusters, what you do is now you do the same exercise over again. You take any arbitrary one of them, you say AB, and you ask, what is the closest neighbor, right? And if needed, you can sort of move it around a little bit. But let's say that in your visualization, you're lucky, these two come and meet, right? They are at the same distance. It turns out, and it may so turn out, that these 3 may all come and meet. They are all at the same distance from each other, right? And it may so be that these 2 are at the same distance from each other, right? So it might represent groupings like this. Are we together? Right. And once again, you replace these pink ones with their centers. So let's mark their centers with a yellow color. The center of this will be somewhere here. The center of this will be somewhere here, and the center of this will be somewhere here. So now you ended up with 3 points. And now, once again, you do this game. You say, you take this point and you ask, what is the nearest neighbor to this? It is this. So you end up joining these 2. And this guy, it turns out that it has no, all the points are exhausted. There is no neighbor you can associate with it anymore. Then what you do is you say, all right, so now these are gone, and I'll replace this with some other color. Let's say this color. So now I have these points, and then this point. This yellow remains, and now, oh, well, actually, I shouldn't use pink. We have used pink. I apologize. 1 second. Control Z. Control. Yeah, so which color should I use? Let me use blue. I haven't used blue. So, yeah, so suppose this and this point now becomes blue, right? And so you have just 2 points. And so the top level cluster would be, so hang on, I did not join the yellow ones. Let me finish joining the yellow ones. Yeah, and so the top level cluster would be saying one cluster that includes them all. And this is it. Right? Do you see how I went from n points? We go from, let's say, we went from n clusters to 1 cluster in a process. I hope you get this process. It will take you a couple of times to review it. It will settle down, but it is important that we understand. All we are doing is we are creating more and more coarse-grained clusters by taking small clusters which are near each other and merging them, agglomerating them.
And the process is, it's a recursive.
It's a recursive process. At the end of it, you'll have just one big cluster. right? And so in some sense, it's the other way around. In K means, remember, we started with K is equal to one giant cluster, looked at its WSS, etc. We kept on going. Now here and there, yeah, you could pick any arbitrary K and start with that. Start with K is equal to 7 if you wish here. But here, you don't have a K. You go through the entire exercise of finding one cluster, two cluster, three cluster, and so on and so forth, right? So then comes an interesting point. The question still remains, what is the right number of cluster? And here is where the answer gets interesting. You have computed clusters at each level of granularity. Now, what people do is that they really appreciate the dendrogram, and quite often they'll print the dendrogram and stick it to the wall, right? So that people can see what things go together, especially in the medical data, what things go together and form, subclusters in the data. So you can look at data at a very fine level, or you can look at it at the cross level. So for example, if I were to, let me draw a cut line. If I draw a cut line, I just need one more color to draw the cut line. Let me use what just happened. This thing seems to have disappeared. Okay, suppose I pick this point, hopefully this is bright enough. We'll see. If I put my cut line here, you see this cut line? Then below that, you notice that each point is a cluster. That is one level of granularity. On the other hand, if my cut line is here, how many clusters do I see? 1, 2, 3, 4, 5, 6, 7. Those 7 pink points, they are clusters. If my cut line is here, how many clusters do I see? I see 3 pink clusters, which of course you see that. And if my cut line is here, I see 2 clusters, which basically says that this cluster and this is the 2 clusters. And of course, so you can actually pick a cut line and decide how many clusters do you want to look at. And you have a full representation of the cluster.
Yeah, so a question.
Yes.
Is this layout, does this layout depend on the type of points you choose, or it's always going to look, the layout will always be unique for a given set of points?
With minor, see, variations are ultimately, right, your system will adapt when you're doing the computation. So suppose you start with CD here. What happens is that the computational engine, realizing that AB and CD clusters are close to each other, it will move it in the diagram close to it. So generally the diagrams are pretty stable, but there is a possibility of, for example, if I laterally invert it, it starts with QR first and AB is on the other side. It's possible. So there's some minor variations that you can have, but in general, what you look for is the nearness of points, not necessarily in what order they have been represented here. Right?
But does it mean that the lower levels which are there, the bottom ones, there's kind of a little bit noise where there might be variations, but as you start going higher and higher, they kind of become stable? Is that correct?
That is right. So in other words, don't be focused on what is the shape of this. What you matter is look at the cut lines and see what clusters they are producing. The clusters they will be producing will be stable. Repeatedly produce the same clusters.
Clusters, I see. Okay, thanks.
Yeah, but now let's think, okay, what are the implicit assumptions we made? There are 2 implicit assumptions we made. One is, what is the distance measure? Well, we already encountered that with k-means. We need to be clear what is the distance between 2 points, and the distance must respect the distance definition of distance constraints, right? And remember, guys, that that definition is invariant. That is true for all mathematics. That's how distances are defined in mathematics. So if you can, please review that. We'll make sure that we'll give you some questions on the quiz to help you review that. But get familiar with that. All of machine learning uses that definition. Now, there is a second assumption that I made, which I glossed over. When I said that you have a cluster, let's say that you make a point. You have a point here, some points here. They became one cluster. There is some other point here. They became another cluster. And then let's say that you have another point, another cluster. You have 3 clusters. You're trying to determine A, B, C, right? So actually, C, I will mark it as even little bit. Sorry, this is not working out very well. Let us say that this is C, right? And A, let me make it a bit closer. Let me cheat so that I can make my argument correctly. So I ask you this question. What is the nearest cluster to A? Like, what is the distance from A to B? Now you can say, well, you know what? Common sense says I go from the, let's say that I go from the center of gravity from here to here. That could be one notion of distance, isn't it, guys? Are we together? One intuitive notion of distance between 2 clusters is distance from the centers.
Yeah.
But what other notions of distance can we cook up?
You can say the distance between the longest points or the closest points in
Right.
the cluster.
Yes,
Edges,
we
yeah.
can ask for the shortest distance between these 2. You know, the distance between the closest points, or we can look at the distance between the farthest points, right? So this distance to here, this distance, right? And based on how you define your distance, see, if you define your distance like this, you will realize that actually A may be closer to C than to B, right? So distances can be, and this definition of a distance, how do you define the distance? It is often called the link function or linkage or something. I think link or linkage, something in your book. So there are a few definitions of this. And based on each choice of how you define distance between clusters, your clustering will change. It will produce different results. And that is something to be aware of. Right? In practice, you have to be careful. And therefore, your definition of distance between clusters becomes a hyperparameter of the model. You can try out different clusterings and see, draw out the dendrograms and then ask which of them looks more intuitive to you from the domain knowledge perspective, which of them resonates with your domain, maybe medical data or whatever it is that you're looking at, which of these clusterings most resonates with the experts in the field, right? And then you pick that. That's sort of that is a small technicality that you have to remember. So now, why would you not use hierarchical or this kind of a clustering? It used to be, k-means is much faster, very fast, it converges. This is more computationally intensive, but these days in modern computers, these classical methods, k-means and agglomerative, are still considered fairly inexpensive methods. But having said that, it's not completely inexpensive. Actually, the computational cost is in higher dimensional space is very high. Like, because remember, a huge number of dimensions. And there are all sorts of optimizations, like for k-means clustering. I told you that we can use KD trees, or in more broadly, metric trees, to use geometric arguments to accelerate the clustering process and so forth. But in any case, this is hierarchical clustering. This is all that there is to hierarchical clustering. Right. So the gotcha is, don't believe that just because B and C are, for example, near each other, it necessarily means that B is closer to C compared to, let's say, Q. Right. That may just be an accident of projecting it on a 2-dimensional page. 2-dimensional representation. Your notions of distance are based on so then the question is, how do I know what is the notion of distance? You would say that B happens to be closer to C because it meets C sooner than it meets Q. Where does it meet Q? It meets Q all the way to the top, right? B meets Q here. B meets C where? B meets C. No, not here. B meets C here. Meets C here, right? So therefore, you would say B is actually closer to C, right? Now, that's how you would look at it. But if you were to ask, is B closer to E or F or G? What would be the answer?
Where the level is, where it meets in the
Yes.
branches as it
Yeah.
goes up the dendrogram.
That's right. So if you look at it, what would your answer be? According to this figure, is B closer to E or G?
It's really
Can't
hard to
say, I
see the
guess.
letters.
You can't say. You would
The-
consider that as far as this dendrogram is concerned, because they meet at the same point here, they meet here, right? B meets E, F, G, H, I, all there. So as far as this dendrogram is concerned, the information that it has is they are the same distance, more or less. Right? Now, there may be minor variations. You have to go back and look at the data and compute the exact values. But pretty much from the dendrogram, you can't say that because I is further away in the dendrogram compared to E from B, therefore E is closer to B. That is not true. Right? That is one gotcha you have to remember in the dendrogram. The distances, if you have to infer distance, look at how far up the chain they meet. Right? How far up the tree they meet, not chain, sorry. How far up the tree they meet, this dendrogram tree. Right? And so that is it. It's a simple algorithm, hierarchical clustering. Now, all of those considerations remain. For example, you may ask, okay, where should I put my cut line? How many clusters should I choose? It's lovely to know that I can pick wherever I want. All the clustering is done, and I can find k is equal to 1 all the way to k is equal to n. Lovely. But how do I, if I have to just say, give me some good number of clusters, the same argument applies. You will do the WS for all of these values. One cluster, this is one cluster, two cluster, let's say two cluster, three cluster, and 1, 2, 3, 4, 5, 6, 7, 7 cluster. And of course, endpoint, of course, will be 0. And you will have to plot out this is the cluster, K cluster. And this is your WSS. And you'll again have to draw a scree plot and hope that there is an elbow. You'll have to draw the scree plot and figure that out. And hopefully, if the data looks like what we just do, you'll find that this happens to be around k is equal to 2 for this particular example that we have. Right? So that's how you do that. And that is all there is to it. This is agglomerative clustering. So after k-means clustering, which took a little while to understand, the agglomerative or the hierarchical clustering is a straightforward exercise. Now I'll give you a homework, guys. Go understand the link functions, right? Or the linkages. Go understand whatever. Why am I mixing the two up? Anyway, go understand those linkages. It's there in chapter 10 of your book. There's a small table. There are 3 or 4. Now the book, the last I checked, and maybe in the new edition they have fixed it. In the previous edition, they missed a couple of the more recently adopted linkage functions in the industry. And so you can read about that, what those are. So take this as an exercise. It's worth knowing what are the available linkage functions and what are their strengths and weaknesses. They have strengths and weaknesses. So read about their strengths and weaknesses.
You mentioned that there were 2 implicit assumptions. One was the definition of distance. I wasn't sure what the second one was.
Is this linkage? When I was saying, what is the distance between 2 clusters? I sort of hand waved in the beginning when I was explaining to you, but then we got more precise and we started asking, what is it?
Okay.
Right? Yeah, and so you realize that you can define it as the distance between the centers, distance between the closest points, distance between the furthest points, average distance between the 2 clusters, all pairwise distances. You can go on, you can go creating all your definitions of distance. There are quite a few valid definitions of distance, so long as they fulfill the distance definition identities, they're all valid. And for each of these, you can then ask, you will get a different dendrogram. Right?
Okay, so the second implicit assumption is that there's a linkage function.
Yeah, no, the second implicit assumption was that we know how to define the distance between 2 clusters. Right, and now that is what we came to. That definition is the linkage function.
Okay, the definition between the clusters.
Yes, of distance between the clusters.
Asif,
2 questions, Asif. How do you decide what's the center of the cluster? right? So suppose when you bring a point, is there just one way of figuring out what that
No,
center
centroid,
location?
the center is again the thing. Once you have a cluster, let's say A, pick the centroid and call it the center. But the non-intuitive thing is, even though you can find the centroids, but you don't necessarily compute the distance between the centroids as the distance. You may have another definition of distance between clusters.
I see. So that's that part. The other part is that over here we have these cuts happening at discrete things, right? 1, 2, 3, 7, like that.
Yes,
Versus in k-means, you have a continuous one, right? You go 1, 2, 3, 4, 5, 6.
that is true.
So is there some notion that between these two, if we do that, is there some learning that happens between these two methods if we do that, or these are kind of completely not related to each other?
See, prima facie, they're not related. But what it is telling you, the reason that agglomerative is useful, it is telling you that we know that the next jump from 3 is 7, right? So don't try to build clusters of 4 and 5 and 6 here, because those would not be very good clusters. See, dendrogram in a way, because starting bottom up, it ends up having more information about the data. Whereas k-means has no information about the data. It just says how many clusters you really want. I'll find it no matter what, right? So that's the distinction between k-means and this approach.
I think so.
Yeah.
We looked at, in terms of the concept of linkage function. We
Mhm.
basically said there are different distances between the clusters. It could be the distance between the centroid, could be the distance between the closest points, the furthest points, could be averages, and so on. Is there a second concept in addition to that, a concept around how do you compute the distance?
No, you always have the distance. We already started. Remember, the first assumption is you need a valid distance between any 2 points.
Okay.
Whatever distance definition there is, now you apply it to this.
Okay, so there are two concepts. One concept we take it for granted because that's the part of the domain.
Yes.
Okay.
That's that. So that is it, guys. It's a simple algorithm. I hope after all the mathematics that we were doing a while ago, this feels much simpler, isn't it? These 2 sessions on clustering hopefully feel simpler. Anybody agrees with that, or this is also looking very complex?
So Asif, I have quick question, a simple question. So I was looking to the CDC data for all the 50 states. So I have a Excel file that has all the states and number of COVID case. So I want to put them into a cluster. So I just have a name of a state and the number of COVID case or death or something like that. So when I'm talking about the points, so that I can find the distance between the points, whether the k-means or hierarchical. So in this case, what is the points? Point would be the number of.
No, see, the thing is,
How do I define the points? That's
see, you must be given data with some coordinates, either the name of the hospital or the name of the city or the name of something. Something must be given. Or the most fine grain is that every person who had COVID, what's his longitude, latitude. Usually you don't get that data. What you get data is at the level of either the neighborhood or the city. So you must be getting X number of COVID cases in this city, right?
But in this case, see, I just have a number of states. I want to say the X, maybe the Florida and Arkansas or some states, they fall into one cluster, other in a different cluster.
Yeah, so the way I would do that is you would take the longitude, latitude of the centroid of the states as representative. You would say that is the location. And US, even though US is a vast land and it's not a straight line, to the first approximation, you can just take Euclidean distance, right? So given longitude, latitude in longitude, latitude, there is an expression for how to compute distance between 2 points. You can look it up. Just use that definition of distance between 2 points, 2 latitude, 2 locations given by longitude, latitude. That will be good enough for you. Is that making sense?
Okay.
Yeah.
Thank you.
That is the best you can do. And so you'll see that there's a clustering, and people have done this analysis. You can look, there are quite a few lovely visualizations people have given. They have given it by lots of cases, like why is it that you have emergence, preponderance of COVID in one location versus another? It turns out that when COVID started, they also started in big cities where there are flights coming in. And it sort of radiated out from there to the countryside. Now we have the opposite problem. For example, the cities are more or less cleaned out, but there is a pretty strong, it's harder to stem COVID in in California, at least in the agricultural belt and so forth. So COVID data is a really good data actually, because we are also aware of it. We have a good domain knowledge. So you would like to play with the COVID data. Many, many good notebooks, data science notebooks you can do with COVID data. And there are lots of data.
Asif, when you said that 2 points are at the same distance from each other, at what granularity are we looking at it? Like,
It doesn't matter. If you have 3 points, let's say that these 3 points, what is the distance? So suppose this is A, B, C. Can you, for any reason, say that B is closer to A than C? So what happens is that it's a rounding error. I mean, you can decide your rounding, but let's say that you're looking
okay.
at distances and you don't, like if you're looking at distance between 2 cities and the flight time, right, or the aeroplane time, you certainly don't want to measure in centimeters. No,
Yeah.
mile could
Okay.
be good enough. So
Okay.
that's how it goes.
Okay.
All right, guys. So that's all I have. If you have any questions, you can ask. The next weeks, the Saturdays, we will do density-based clustering, which is a little bit more formal way, but it is actually the most. At the end of the day, I find as a physicist the most intuitive. But we'll come to that.